Okay, so let's start. Okay, so we're going to continue the OpenMP lecture today. So sort of trying to wrap up today, maybe a long lecture, so it may go into Friday, and then on Friday I will give some sort of examples on how to use these techniques on various problems. So essentially, you know, the OpenMP is, you know, at least the basic concepts, you know, are fairly straightforward. So essentially, you have two main concepts. The first one is just the for loop. Okay, so how to parallelize the for loop. Although, as I pointed out, there is no magic here. The idea is, well, if you have a for loop in which each iteration is independent, then you can just parallelize it with pragma OMP parallel 4. And if you have dependencies in your for loop, essentially you need to rewrite your for loop or do things slightly differently so that, you know, each iteration becomes independent. Okay? So sometimes, you know, it's really just more than adding this one line. It can be changing the algorithm. But, okay, this is the basic thing. And then the next idea is concept of task. So obviously not everything is in a for loop. I mean, that covers the vast majority of cases, but let's look at situations where you do have a lot of parallel work, a lot of concurrent work, but it's not in the form of a loop. Okay, and so this is a little bit similar to the C++ thread concept of, you know, you have a certain block of code you want to execute and you're going to assign it to a thread. Okay, so there are, you know, a number of sort of classical examples of, you know, using tasks. So essentially, you know, you need some sort of a process in which, you know, a lot of independent tasks are going to be generated. Of course, you could generate just a handful of tasks, maybe 1, 2, 3, 4, but then, you know, you're going to be limited in the concurrency you can express in this process. But you have situations where, you know, you can actually, through tasks, still, you know, provide a lot of concurrency. Okay, so for example, tree traversal. So it's a sort of a recursive process. You can generate, you know, a large amount of concurrent work, and then use the OpenMP task for this process. So classical example of tree search, you know, is if you try to play a game, so a game of Go here, okay, and in trying to build a tree of all the possible moves from the current configuration on the board. So each move is basically adding a new stone. So say it's black's turn, so you're going to add a black stone here on the right, or the top right, and so on. And then next one is the white's turn, so maybe you add a white stone here, or middle right here, and so on and so forth. And so you know, you can go down a couple of steps and try to enumerate, you know, all the possible combinations and try to figure out, you know, what is the move that has the highest probability of winning. Okay, and so essentially there's two processes in this, you know, in this calculation. One is the actual traversal of the tree. So essentially each node, you know, looking at the children nodes, and then each, you know, child node looking at its own children, and so on, just, you know, traversing this. And then presumably there is some sort of calculation or evaluation that needs to be done at every stage. So for example, it may be, you know, you could have an algorithm that suggests, you know, the next top 5 moves that you could try from here. And then you would try, you know, these as 5 children, you know, 5 different options here at the bottom, and just keep going like this. Okay, so this is the problem of tree traversal. So for certain types of tree, it is possible to write a for loop. For example, if you have a completely regular tree where each node has a fixed number of children, then, you know, you can actually write for loops to kind of traverse what's happening at each level and so on. But if it's a very adaptive tree where the structure is sort of not really known or is not very simple, then you need something a little bit more sophisticated, right? So the for loop is not going to work well in that case. Okay. So I'm going to show you, an example. So if you want, you can open up this code on GitHub. So I'm just going to show you the snippet of code. But if you go to GitHub, on the code lecture 5, then you're going to have the code samples I'm using for today. Okay. So I don't know if this actually works. See if it works. Okay, yeah. So this is an example of a routine that would traverse a tree. So it's a binary tree. So you have at most 2 children, but not the 2 children nodes do not necessarily exist. So the way this works is, first of all, this is sort of a recursive process. Okay. So you are sitting on a certain node. So you're going to start from the root node. Then there is this function visit. Basically, this means perform some operation on the current node, so some calculation of some type. Okay, so you do this before visiting the children node. So it's called pre-order traversal. So you visit the node and then traverse the children, and then you ask, well, so it's a binary. So you have a left and a right child node. So does the left node exist? If so, then traverse it. And then does the right node exist? If so, then traverse it. Okay. So here we are assuming that all these visits are independent of each other, can be done concurrently. So you can see that you can generate a lot of visits at every node of the tree. Okay, and run this concurrently. And so this is what happens. So traverse might be a task here when you start, and then it's going to generate 1 or 2 other tasks. Okay, and then it just keeps going. So if you do this a couple of times, then you can generate a large number of tasks, and pretty soon, all the processes or cores, have work to do. Okay, all your thread pool have a task assigned to it. Okay, so now this task is similar to the C++ thread. Okay, in the sense that when OpenMP encounters traverse, what this is saying is, okay, well, here is a piece of work that needs to be done. It's independent of everything else, but you're not specifying, how this is going to be, like who is going to run this and when. Okay, and so different scenarios are possible. The main thread, if everybody's busy, the main thread might actually execute traverse itself. Okay. Or it may be a deferred execution, which is sort of perhaps more what you would expect. So in the sense that it records that there is this task to do, and then continues on, the main thread just continues on with the rest of the code. And then, either that thread comes back and executes traverse, or some other thread, starts executing traverse. Okay, so it's deferred execution. So presumably, initially, you have one thread that starts from the root node, then execute 2 subtasks. So after that, maybe you have 3 threads working. Then each thread, perhaps generate 2 other tasks and so on. So you just keep doing this until essentially all threads or all cores are busy. At which point the execution sort of becomes sequential again. Okay? Instead of setting aside the task or giving it to another thread, then once you have a lot of tasks in flight, then the thread will simply start executing this as if it was a sequential code. Okay, so this is basically the process here, and so now, so you cannot call the function traverse just sort of just like that. Okay, you need to put something around it. Okay. And you need to do 2 things. The first one is this needs to exist inside a parallel region. Okay, because remember, essentially the program is split into a sequential part and a parallel part. So in the sequential part, there's only one thread working, and if you write OpenMP task in that region, probably nothing happens because there's only one thread running. So there's nothing happens. So you've got to be inside a parallel region, okay, where like, all threads are now active and potentially could do the work. Okay, so pragma OMP parallel, and then you traverse, traverse root. Okay. So next thing is a little weird, and it sort of goes back a little bit to I guess the way OpenMP came about and sort of the historical baggage, which is that when you encounter pragma OMP parallel, well, not only are you declaring, okay, well now I have multiple threads and they can execute the code concurrently and so on, but in fact, in principle, if you remember what was said last week, inside a parallel region, all threads are expected to execute the code. Okay, so if I don't say pragma OMP single, then actually all threads will do traverse, which is not what you want. Okay, what you want here is you want to create a pool of threads, multiple threads that are sort of available to do the work, but the code traverse itself is only executed by a single thread. Okay, so it's a little, maybe counterintuitive or whatever, but only one thread actually needs to execute this code. Okay, and the logic behind this is, for example, let's go in traverse again. When you encounter this, only one thread should do the root, and then essentially one thread is going to create this task, and one thread is going to create this task. Once you have these two tasks, those can run in parallel. But the process of creating the tasks is done by only one thread. In some sense, the task is created only once, right? Without the OMP single, you'd have and you had, let's say, 4 threads, you'd have 8 tasks, and 4 of them would just be repeat. Okay, so clearly this is not what you want. So always remember, when you use task, essentially you have to be in a parallel region. Okay, pretty obvious, but you must include OMP single. Okay, so this is sort of a common error, and without OMP single, essentially you would traverse the tree 4 times, which doesn't make a whole lot of sense. Okay, so basically this is just kind of a summary of this. So either the thread execute immediately the task or defer the execution, and then in terms of who is executing the task, well, it's anybody in the thread pool. Okay. So any question about this task? So it's basically like C++ thread, but instead of having to write an actual function, it's just a block of code. So it's kind of neat in terms of the syntax is a lot simplified. Although to be honest, with the new C++ 11, you have lambda functions. So it is possible in C++ 11 to create a thread and sort of right there, write the body of the function that needs to be executed with lambda function. So it would look actually quite good. But regardless, this is a bit more flexible. And again, one thing that is quite different is that C++ thread, when we say thread, a new thread is actually created. Whereas when you say task, you may have a pool of thread that's already live and running and just sort of waiting for things to be done and just to hand it, a new piece of work. So in some sense, this can be done much more efficiently. Okay, so let's look at another problem now. So we did the pre-order traversal, meaning that you visit and then you traverse the children nodes. Okay, so the way I wrote the code, it was it was very clear. The main thread enters traverse, runs the function visit. Once it finishes, then it encounters the task construct and just goes on. So this is sequential. The task must exist after visit. Okay. But how about another situation in which you visit, okay, and then you execute something, okay? So actually, sorry, I didn't show this correctly. So for this node, it would be more like traverse the left child, then traverse the right child, then visit. Okay, so it's more like, well, it's a funny drawing, but okay. It means you visit left, visit right, and then you do something. Okay. So for example, if you want to do some sort of reduction, okay, where your maybe some scalar quantity is attached to each node, and you want to just sum up all these numbers. Okay? So you would say, okay, well, I need a number for A, I need a number for D and like the entire subtree. Once you have these numbers, you return them, add the number for B, and then you continue. Okay? And so this process of adding and sort of returning needs to wait for the counting of A and D to be complete. Okay? You cannot do this. You cannot just say, oh, visit A, visit D, and then return. Okay? You obviously need the result of counting A, counting the subtree D, and then you can add and return. So that's again another common problem in multiple computing, which is synchronization. So basically, there's a so-called synchronization point. Okay, by synchronization, I mean that you declared that there is work to be done for subtree for A, there is work to be done for subtree D. Okay, so some threads are going to do some work. Okay, it's done concurrently. It's a deferred execution. Okay, you need to wait for this to be over before you can continue. Okay, so it's called synchronization point, to basically wait for the other thread to be done before you yourself can continue your work. And so there's a special pragma in OpenMP that will do that. Okay, so you're going to wait for the children to be complete before continuing. So this is so-called tree post order online. You want to see the code, but this is sort of the bit that matters here. So it's called post order traverse. So it's basically the same as before. You have pragma OMP parallel, you have pragma OMP single. Okay, so now you're traversing the tree. But what this is doing is it's counting the number. So the scalar quantity on the left. So here just the number of nodes. So just just counting the nodes. So how many nodes you have on the left subtree? How many nodes on the right subtree? Okay, so it's the same as before, but there's a couple of differences. First of all, so similar to C++ thread and so on, all variables that appear inside the task, are private. So in fact, specifically, first private. Okay. So this is saying that, for example, you may have. But here the block is just a single line, so it's very simple. But if you have a block of code, you may have local variables and so on. Those are obviously private. But let's say, what about left here? Because left is defined before the construct. Okay. So usually left should be shared. Okay. If you just have a pragma OMP parallel, okay, before the parallel region, these are shared variables. Okay, so you'd expect left to be shared. But tasks are a little different, right? Because what's happening is when you have pragma OMP parallel, you have a parallel block that begins, okay, and then this block ends, and there's a synchronization point at the end. So it's kind of clear where the parallel region starts, where it ends, and and it's kind of logical that if you had variables previously defined, they would be shared. But for task, this is a little bit more involved because you don't know when the task is going to be executed. Okay, it gets shipped off and executed whenever. In fact, it's very possible that post order traverse returns, okay, while the task is still not executed. Okay, and so for example, if you look at left, and so as a result, for a task, it makes more sense that things should be private, like everything should be private, because things that are shared obviously trickier, because again, you don't know when the task is being executed, so you have to be very careful that, for example, if there's a shared variable in task, that the task is complete, say before you delete this shared variable, otherwise there would be memory corruption. Okay, so the default is to be private. Okay, and so for example, left, the default attribute for task is it should be first private. Okay, and first private means that it's private and then it's initialized with the value before the constant, so basically 0. Okay, so start with left equals 0, well, the initialization here doesn't matter, but okay, whatever, it's first private. And then it becomes private, you know, inside the task. But in this particular instance, that is not the correct choice, because you need left to be updated here. If left is private, then that thread, the task is going to calculate left, but then right here it's going to be 0. Okay, because, you know, private copy, right? So actually left by default is first private, but you want it shared, so you have to specify shared. Okay, so shared left and shared right. So again, you know, if you have pragma OMP parallel, the variables by default are shared, but for tasks, the variables by default are first private. Okay, so this is a very important difference. And again, you know, if you're not really paying attention and you have these default choices, you know, could lead to some error. Okay, and here the error is left and right would be always equal to 0 without shared. Okay, so everybody's clear about that? Yeah. All right, so that's the first point, shared, and then you know, you have pragma OMP task wait, meaning that the code is going to stop here and will not execute this line until both these tasks are complete. Okay, so whatever tasks, you know, were declared prior to task wait, you know, in this function right here, you're going to be waiting on that. Okay, and so now you know that once you execute this line, you know that left and right are to date, and you can just sort of continue with that. Okay? Yeah.
How does it know it's those two tasks it's waiting on? Is it like a scoping thing?
Well, yeah, basically, there's some complicated rule that I can never remember, but yeah, basically, right. There is a definition of what are the tasks that, so essentially, right, so I don't remember the definition, it's actually a little complicated. One of the points is that, for example, well, something I know for sure is that, let's say that this task right here declares other tasks, you're not going to be waiting on that. Right? So for example, so here post, you know, so if this guy was doing other tasks, but then just returning, then you would just wait for the return, not the completion of all these like children tasks or whatever. So yeah, there's a complicated way to understand like which task you're talking about. So you know, maybe a potential source of errors. So for sure, the children tasks are not included, but clearly, you know, there might be tasks that are called like prior traverse. Okay, and I'm not 100% sure about that. Most likely, you're not waiting on that. But yeah, there's some the compiler. There has to be a convention as to what you're supposed to be waiting for, because task wait means you need to, the compiler needs to register like what task it's supposed to be waiting on, obviously, right? And so there's a little bit of work as to, you know, when you encounter OMP task wait, you need to register, you know, what you're supposed to be waiting on. And so, for example, if there are other tasks outside of post-order traverse, you know, that at least becomes sort of arbitrarily complicated. So my sense is that they may be excluded, for example. So yeah, there's a little bit of complexity. I mean, I can double check on this, but yeah, I remember looking into this, and the answer was something which at the time I understood, but I forgot now. But yeah, there's a little. There's actually a lot of things of that type, like scoping things that are very opaque and kind of technical. Okay. So yeah, but good question. Yeah, good question. So then you have first private. So we talked about this, and then task wait. Okay. So let's look at. So here, you know, the process of generating tasks is basically a recursive calls. Okay, so this is sort of case number one. Case number two is basically a while loop. Okay, so while loop is also something that would be difficult to parallelize. Okay, so unlike so a for, although the for loop, in some sense could be types of while loop. I mean, the termination condition could be kind of complicated. But what's happening is when you say OMP parallel 4, then the API specifies that the following loop should be simple. Okay, so essentially, in the case of for loop, everything you should be able to reason about the loop, like you know when it starts, you know when it ends, you know exactly how many iterations it has. Okay? So everything is sort of known ahead of time, so the compiler can do some optimizations. So here we're looking at basically an iterative process or a while loop, but where you're passing a list, so you don't know how many elements you have in your list. In that case, the pragma OMP 4 does not apply. Okay, and this is another example where tasks work extremely well. Okay, so again, very similar construct: pragma OMP parallel, pragma OMP single. Okay, and so you just traverse your list. So here it's just I did the list sort of by hand. You can use the SCL and so on. Doesn't matter. So essentially at the end, current node is null. It's going to stop, and every time you visit a node, you have pragma OMP task. Okay, and then just visit the next node and so on. So in this code, for example, well, it's a very simple code, but still it is possible to have bugs. In particular, you can see that current node keeps changing, right? Because it keeps moving in the list, right? And so when you say pragma OMP task, you say visit, but the argument is the value of current node, okay? But current node keeps changing. So what value is that? Okay. So this is where this default choice of first private works as it should. Okay. So what's happening is current node is defined prior to task. So the default choice is first private, meaning that this block of code here will have a private copy of current node, and the value will be initialized by the value of current node prior to entering the construct, okay, which is exactly what you want here. So actually, in this case, without doing anything, you get the current code, but the correct code, but you see that there is actually a solve point in the middle. Okay, so I guess this is it. All right, so any questions about this? Yeah.
Is there a way to execute a particular task or to wait for a particular task? Like if you spawn a whole bunch of tasks and then you want to wait for one of them?
Okay, all right, so good segue in the next bit. So now, so I guess until recently, so I haven't tracked exactly the specifications or whatever, but until recently, there was only task wait. I mean, until actually, there was some time ago when there were no tasks, so tasks was sort of a recent addition, and there was sort of limited support. And so initially, that's right. The only thing you could do was this task wait, meaning you wait on everybody. But there are situations in which you want more fine-grained dependencies, and the reason for that is so that each time you do task wait, it's a synchronization point. Okay, meaning you gotta wait, right? Like no additional work is going to be produced until everything that comes before is done. But it may be the case that actually there are tasks coming after that are ready to be run, right? And you're just waiting for no good reason. Okay, so it's very important that when you declare a task, you sort of specify the minimum number of so-called dependencies, okay, so that you start essentially as soon as possible. As soon as essentially the input variables for a task are ready, okay, you should go, okay. And so how does this work? So this is rather, this is more complicated, definitely bug prone, but in the recent, maybe 4 or 5 version of OpenMP, you have now this fine-grained control over tasks. And actually, I'm not going to go over everything, but just at least some of the features. So first thing is priority. Okay, so priority is something actually a little tricky, but so actually let me just little aside here. little aside, which is so-called, so-called critical path. Okay, so critical path is basically a situation like this, where you have a sequence of node like this, and so here this is a path, and what this diagram means is that you cannot execute the next task until you're done with the previous. Okay, so now let's assume that you had a situation like this, where you had at the top. So at the top you have many tasks. So of course this is a little kind of exaggerated, but okay, let's say this goes like this. Okay, so essentially as soon as this task is done, then you can execute all these tasks. Okay. Now the question is, so what about this priority? Okay, at some level, all these tasks you can do, and you can start with whatever and so on. Like what difference does it make? Well, so there's this concept of critical path, and the critical path is basically in your graph. It's the longest, essentially, sequential path. Okay, and so by sequential path, I mean that you have an exact sequence. And so, for example, you may have 1 million cores, but if the only thing you have to do is this guy, only one core is ever going to have any work to do. So critical path is basically, saying that let's say you have an infinite number of cores. That's pretty much the fastest you can go, okay, or that's the lower bound on execution time. You cannot go faster than that. And so the best you can do is therefore to do this as quickly as possible. In the sense, you start here. As soon as you're done, you move to this guy, then that guy, and that guy. Okay. Now you have an infinite number of processes, of course. So while this is happening, you can assign one core to this. Okay. Right. And then let's say that all these circles take about the same time to execute. Essentially, once you're done with this one, then actually everybody's done, and you go here. Okay, and indeed your execution time is minimum. Now the wrong thing to do would be to not start this task right away, but for example spend a lot of time doing all these tasks. Okay, and once all these are done, then you start working on this path here. And the reason why this wouldn't work is because then at the end of your code, you'd have one thread doing work and everybody else just being idle. Okay. So this leads to the concept of priority. It means that it is much more important to make progress on this critical path as soon as possible, whereas these can be done just whenever a thread is idle, you can go work there. But it would be very bad that, for example, a task here has to wait for one of these guys to finish. Okay, that's suboptimal. So you want these guys to have high priority. Okay, and these guys to have low priority. Okay. So there are different, priority is kind of a complicated business actually. So that's sort of theory. Now, of course, in practice, yeah.
What if all the paths have equal priority? And won't the threads...
Oh, you mean like all the critical paths are the same length? Well, equal priority means basically everybody has the same length. Right? Like there's no one that's shorter than the other or whatever.
How is priority related to the length? I didn't get
Okay.
it. Yeah.
So so what this is saying is, right, so when you're deciding on which task you want to execute, so let's say you finish this one. So then, you have one of these 7 tasks to choose from, right? So you have a pool of tasks that are ready to execute, and you have, a scheduler or something that's going to decide, say you have 7 tasks, but you have only 2 cores. So you've got to decide which one is next, okay? And so if you don't have any priority, typically it's random, like whatever. But you want this to have a higher priority. So let's say priority is 0 here, priority is 1 along here. Okay, so if you have a choice, you pick 1. Okay, and then the next thread would be 0. Okay, and as soon as this one is finished, next highest will be 1, and so on, just keep going. Okay, so in your algorithm, the critical path should have a high priority, whereas the sort of side branches, if you wish, should have a lower priority. Okay, so that's the. But you can see that it becomes arbitrarily complicated, right? Because you clearly don't have an infinite. If you have an infinite number of processors, that is really the only thing you care about. But you may have a certain critical path here, but then on the side you may have another path that might be shorter, but it's still kind of long, and it would be the second highest priority and so on. You can see how the scheduling problem becomes complicated. So the bottom line is this is something that can be used, but it's very hard in practice to figure out what should be how to assign these priorities. Right? Sometimes it's kind of semi-obvious, but it can be something to play around with, and it's very, for complicated code, it's very hard to figure out what the priorities should be. But there are cases where let's see. Well, there are cases that are semi-obvious. For example, if you have a task that runs for a very short time and then leads to the creation of one or many tasks that are much longer, then you probably want to give it a high priority. Essentially, it runs very fast and it unlocks a lot of work. This would be a trivial case where you want a high priority on tasks like that.
Well, even I think this example, you can pretty easily see that if you start traversing the longest path first, if you assign
right.
one core, if let's say you have 2 cores and you assign
right.
1 core to that, yeah, I mean you can see that you can do, like let's say each circle is a unit of time, you can do it in 6 units of time.
Right.
If you start outside and go, then I think it should take like 8 units of time. So.
Right, but although, for example, here you can also realize that, right, of course, if you were to do the 6 first, and then finish here, it would be 6 plus whatever, 10 or 11.
Well, it would be 4. Like, let's say you have 2 cores, and let's say.
Oh, yeah, right. You have 2 cores, so you have 1, 3, 4,
and then 8.
Right, 8. But for example, in this example, if you only have 2 cores, you can see that this takes 4 units of time, but this takes 6 units. So it would be actually okay for core 1 to do the wrong priority a couple of times, but because you just don't have so many processes to begin with. So there's some leeway. Well, anyway, I mean it's kind of a complicated thing. I don't want to. Plus, this is just a. Right, the priority also is just it's just a hint, right? Because what's happening is in this example maybe this is too simple, but if you generate, for example, yeah, okay, I don't want to spend too much time on this, but this is just a hint. So meaning that you want a task with a high priority will tend to run sooner, but there's no guarantee that this will happen. It's just sort of a hint you're giving the system that if there's a choice between 2 tasks, it will pick the one with highest priority. Okay, so now let's go back to the other question, which is these dependencies. And so essentially, for dependencies, there are 2 things. There is a lot of stuff around for loops, which I actually am not going to cover, where you have you have many loops, many cases of for loops where there is actually dependency between I and I plus 1. Okay, you need to wait for the previous iteration before doing the next one, but there's still a lot of stuff that can be done in parallel. So there's a way to kind of describe in a more fine-grained way what is dependent in the for loop and what is parallel, so that you can extract some parallelism, even if there is something that seemingly sequential. Okay, but only some parts are sequential. Okay, maybe other parts are actually parallel. So I'm going to skip that because it gets really complicated. But I wanted to cover this because this might be a little bit more straightforward. And so so essentially you have a clause. It's called depend. So let me just show you an example. Where when you declare a task, you can include dependencies. Okay? And the way dependencies work is you specify variables. Okay? Or, so it's actually memory locations. Okay? So basically a pointer or some location memory that's going to sort of be used to reason about the dependency. And the dependencies, so you go like this: pragma MP task, okay, shared X, because otherwise it's first private, and then you have this depending. Okay, and the depend has name of the variable, so it could be arbitrary variables, arrays, what have you, and then you have out and in. Okay, or actually the list of keywords was shown here. You have in, out. So this vaguely reflects. Okay, in means that the task, in order to start, the task needs the value of X to be up to date. Like if there were previous modifications to X, they need to be completed. So essentially, there was another task that was modifying X, then that task needs to be done before the in task starts. Okay? And then out means that the task is going to modify the variable. Okay, and in and out is sort of doing both. And then there is, on top of that, mutex, which is similar to what we saw, which is basically mutual exclusion. So you cannot run the two pieces of code at the same time. So that's the sort of mnemonic, or the sort of a little bit the meaning of this in-out. But specifically, so I'm going to show you then now how this works. There's actually a table that defines exactly how this works. So for example, the in keyword means that if previously you had a task that had the same variable but without, then there's a dependency. Okay, this one needs to wait on completion of that one. Okay, if you have out, then you need to wait on everything else. Okay. So essentially, this is saying you're going to overwrite X with a new value, but a previous task requires a value of X. So it needs to have, use that value, and after it's been used, you're allowed to overwrite it. A little bit less obvious to me is out also depends on out. So for example, if a thread writes X equal 1, another thread writes X equal 2, there's actually supposedly a dependence. It's so weird because you're going to overwrite. So like, what's the dependence? But okay, the specification say that that is a dependence. Okay, and then the mutex is actually so it depends just on in and out. So for example, so this is so the previous case actually. So this is terminology. I didn't write it down because it's not super important. But this is what's called a dependence. Okay, because it's this guy is going to produce X and this guy is going to use X. Okay, and X is always equal to 2 because of the out and in. So it's called dependence. And then there is the reverse, which is called anti-dependence, which is the in and the out case. So anti-dependence means that this task needs X, the value of X, so X equal 1, and this task here is going to modify X. So hence it has to run after, so that this guy sees the correct value 1. Okay, so it's called anti-dependence. Okay, so this is the in-out case. Okay, and then you have the case of mutex, which basically defines that the tasks are can be run in any order, but not at the same time. Okay, so it's basically just like the concept of mutex. Okay, only one task. So basically here, you have mutex on C, so same memory location, same variable. So there's an exclusion between these two tasks. Okay, so now we're going to do a little game. Going to do a little game. Okay, so I need to set this up. So you need your phone to play this game. Let's see if I can do that. Okay, you need to go to this website. So actually, I need to start it. So hold on. Let me just bring it here. So you need to go to this website, Kahoot, and with your phone and create. Actually, I'm not sure you need to create an account. So let me just start this. And there's going to be funny music and stuff. Okay, so let me just start. Okay, so I'm going to do this. Okay, so can I show you? So it's a little complicated because I need to show you the game and the code at the same time, because you need basically the code to answer the game. So hopefully this kind of works out. Whoops, sorry. Mistake. Where was I? Okay, so hopefully this is, yeah, I don't think I can zoom in. Okay, but hopefully you guys can see it's big enough. Okay, so, all right, so I guess you guys see how it works. So you go to this website, you enter the game pin. So actually I'm going to try to play as well. And so you can have, so hopefully you guys can read the code, but there's going to be some questions about the code that you need to answer. And so if you have questions, ask right now, because you have 30 seconds to answer each question. And then you get a score at the end. So I think I already played this with some of you. So I enter the pin. So there's no icon at the bottom where you enter the pin, so I guess I'm really. Okay, then you have to pick a name. Well, I'm gonna, of course, no offensive name. To be honest. So Eric, that's me. Well, you don't have to put your own name, obviously. R++, okay, that's nice. So, okay, 14 players, so I think that's all of us. Okay, so now I need to remember. Need to remember how to start. Sorry, I need to. It's so tricky with the window. So you have 30 seconds to answer each question. So don't be too stressed, but it does go fast. Okay, so let's start. So are you ready? Okay, 6 questions. And so you press basically on your phone. So question mark, task T2 comes after T1. So this one comes after this one here, and you have to pick one of the answers. Okay, so this is how many people answered, and then you have the correct answer, and you score. Okay, this is the easy question. We should get it correct. So yeah, sometimes. All right. So before going on, so here there is a depend out A and depend out C. So these are completely dependent. Okay. So A and C different. So basically this comes at any time. So basically sort of non-committal sometimes. Okay. All right. Any questions? All right. So we just have 6 of those. Okay. So actually it's supposed to be some music. Just kind of entertaining. I don't know, maybe it's not working. Okay. Actually, let's get the music. The music is kind of fun. It's not. Let's see what the sound is coming out of. Do that. Well, I don't know, maybe
Maybe a volume slider on the actual machine itself.
here?
Yeah, I don't know if there's actual volume.
Because they're either.
Well, that's fine. Yeah, I don't know what's wrong with the sound. Okay, so that's the scoreboard. So yeah, the score is dependent, of course, correct, also how fast you are. So I guess Smart was the fastest. Okay, so number 2. T2 comes after T4. So T2 is here, T4 is here. So T2 and T4. The F is for a genius. It's a weird feedback. All right. So answer is never, right? So actually, I sort of wrote it backward. T4 has a depend in A, right? Whereas T2 has an out A. Okay, so basically T4 must come after T2. So I sort of wrote it backward, and so the correct answer was never. Okay, so actually still number 5 wrong answers. So you have to be more careful. It's not graded. So Mart is doing well. I'm number 3. Yeah, that's pretty good. So T5 comes after T1. So T5 is this one here. And T1 was that guy over there. So it will be more complicated. So obviously, you're kind of new to this, so maybe you have to think a little bit about this. Yeah, the sound is it's more fun with the sound. It's confusing. Okay, so all right, so I guess fewer errors. So this is you guys are getting it. So yeah, task T5 has the Mutex C depends on as it depends with the out C. So it has to come after. That's a must. Okay, so that's correct. All right. So Mart is still the fastest. And T4 and T5 may run concurrently. I guess. Not sure how many pairs we have. Okay. So no, right? Concurrently means that they can run at the same time. Okay. So where concurrent means they can run at the same time. So that's basically the point of Mutex in outset. They can run in any order, but not at the same time because you're updating the shared variable C. So answer is not possible. Okay. So you also have a streak. I got a streak. Meaning that if you keep answering correctly, sometimes in a row, you get a super bonus. So it can pay off to be slightly slower if you can get a streak. But I guess it's still number 4. All right, and last question, I think. Oh, no, 5 or 6. T5 comes after T1 and T3. The T5 is right here again. And talking about 1, which is this one, and 3, which is this one. Okay, so 1 before. Okay, all right, so exactly. So here it's a little tricky. You have the in B means that T5 waits on T3, but then you have the Mutex C, which means you also wait on T1. Okay, so you have to come after both because of the Mutex and the in. All right, and last question is, right, so F has a streak of 5 correct answers so that I can is on fire. Okay, this program prints d equals 6. So you have to kind of go through the steps here. Okay, yeah, right. So yeah, I could have given you the incorrect result. I thought it was 6 was the correct result. Okay, awesome. All right, so we're done, and so just have the final podium. Look at this. I guess it's Ryan and the mysterious Mark. I don't know who Mark is. Woo! You know who's Mark? That's okay. All right, okay. Oh, it's dancing and so on. Okay, cool.
Oh, nice.
I can put you. Okay, all right, so we're good with that. So that was Mutex in and out set. All right, thanks for playing. Okay, so that's that. Okay, and so we're just going to wrap things up with just a couple more things. So first one is reduction, which actually is something you need in your homework. So not super complicated, but just make sure that in your homework, there are a couple of questions about reduction. So make sure you use that. Sometimes students, find other ways to get, the answer. But so this is the most efficient implementation. So make sure you use that. So basically, reduction has to do with the following code. And this code is obviously, this type of code is very important. You're just going to calculate the sum. You traverse some array, compute certain quantities, and you calculate the sum of all these numbers and end up with one result. Okay, so sum. So every time you do, for example, calculate a norm, if you do a dot product, okay, well, obviously it's a sum. If you calculate like the 2 norm, or the 1 norm, or even the max, okay, all these are examples of sums. If you do a matrix vector product, you're going to have a sum. I mean, depending on how you parallelize. And so the key thing is there are two issues with the sum. First of all, there is a race condition on sum. Okay, so if you have all the variables sort of reading and writing to sum, that would be wrong. Okay, so there's a race condition on sum. In fact, if you just look at this loop, seemingly there is a sequential dependence because you need to read sum, add, and need to write the result. Okay, and so there's sequential dependence. In addition, different threads need to read and write sum, and this is very bad because the sum, for example, cannot stay in register file. Okay, it needs to be flushed back to memory so that another thread can then read it. Okay, so it's extremely slow. But there is so there's a problem of correctness and efficiency. But there is a much better implementation, and this is basically what I explained first day of class, which is you can have each thread compute make its own local copy of sum, okay, do its own addition in its own local copy, and then let's say you have 2 threads, then you would end up with 2 sums, sum 0, sum 1. Then you need to add those up, and that is the final result. So there's an obvious path to parallelizing this loop very, very efficiently. Okay, just local copies of sum, and then once you're done with the code, you just add all these partial sums together, and you get one final result, and that's the result of this calculation. So there is a correct and efficient way to implement this, and actually the beauty of this is the compiler needs to know almost nothing, okay? Because the only thing the compiler, needs to know, it needs to know that there is this variable sum, okay? And so each thread needs to have a private copy of sum, fine. point number one. And then second, the operation to be done at the end, once you have all the partial results, is a summation. Okay, that is the only two things. Actually here, you could have really very complicated code, right? There might be several pluses and so on, maybe even minuses or whatever, okay? But the point is, you would get a private copy, everybody does the calculation, and then all these final results are just sort of added together, okay? And so this is specified exactly here. What is the operation that you need to do at the very end? And, what is the variable in question? The variable is sum, okay? So here you can have multiply, you can have bit operation, and so on. You can have minus, which is basically just a sum, but you get the negative at the end, you get divide and so on. So different operations, and then whatever variables you want. So typically these are scalar variable. These cannot be arrays, although maybe in recent version of OpenMP this can be arrays. But typically this has to be just scalar variables. Okay, so there's basically two questions: race condition, and then improved efficiency. Okay, so now, so there's just a couple more things I want to do. So now a little exercise for you, just very briefly. So if you want these slides, they're on GitHub, so you can see the syntax for the parallel 4 reduction plus column sum. Okay, and I want you to do something similar for this piece of code. So I'll let you download, and so you can download this file, and so there's a make file in lecture 05. Okay, so you can go GitHub code lecture 05, and then it says entropy and entropy solution. And so just open up this code here. So it's not terribly difficult, but you have to compile. And then there's a number of loops that I want you to parallelize. Okay, so remember it's pound pragma OMP parallel 4 is how you parallelize a for loop. But then in the middle, you have this operation. So basically, calculate the two probabilities, okay, and then the entropy of each probability. So first you have to normalize the probability. So it's going to be a sum, okay, and then you're going to normalize each entry, and then computing the entropy of each probability, each distribution. So here sum, there's going to be a reduction. So reduction plus, and then you can say sum 1, comma sum 2. Okay, just list all the variables for which there's a sum. Okay, another parallel 4 to normalize entropy, and then finally calculating the entropy by just the sum of P0 times log P0 and P1 times log P1. Okay. So it's minus P log P. And then just print. So this is a result that the entropy difference should be this. Okay. So basically 3 for loops. I'm sorry. Wait. Four loops. Four for loops and 2 reductions. So hopefully everybody's okay with the compilation step. Has anybody played with Google Cloud yet? Nope. Oh, you yet? Right, So the instructions worked as advertised?
Yeah, the script worked, that's what they created.
You can just open the okay, well, I guess half of the students have their computers, so maybe we'll spend too much time on that. So the compiling is working. So I'll give you a couple of minutes and then just show you the solution. Let me just wrap it up here. So let me know when you're done. Like once students finish this. Are you done? Okay. So what do you use to compile? You on the Mac?
Oh, yeah, no, on the terminal.
Like which compiler?
I use G++ dash. So
Oh,
that's
C++. Right, I see.
Oh, yeah, that's right.
Okay, so yeah, the only thing is here you can simplify the reduction by saying N1, comma, N2. Oh yeah, you can also just repeat it. Okay, everything else is done? Let me know if somebody else is going. Everybody done? So one thing that actually, yeah, if you want to try something, the next thing to try is when running this code, you're doing this reduction, and so the order in which the additions are done can change, right? If you have one thread or two threads, the order of summation is going to be different. So as a result, the round of errors are going to be different. So you can try to run with just a single thread or run with two threads and look at the results, and you will see that they differ by basically machine precision. Okay, so you can use OMP non-threads, so you can export OMP non-threads, or you can use the OMP command OMP set non-threads to change the number of threads, so let's say go from 1 to 2, and then you will see that the results change. So you can do that if you want some more advanced exercise. So let me just show you the solution.
Would it possibly give different results for if you run it twice with 2?
No. Oh, if you run, no, well, that depends on the scheduling. Let's see. I would say no. So in this case, no, because the scheduling is most likely static. So it's a deterministic scheduling, so it would just repeat the same. Right? I mean, you have round of errors, but obviously if you do the operations in the same order, then it should work. But there are definitely cases where, for example, if you were to do dynamic, well, there might be some slight variations in the ordering of threads. But static, for example, would just repeat exactly the same thing. Okay, so so this was the solution, but it's so you have pragma OMP parallel 4. Okay, so first you can Right, so you have pragma OMP parallel 4. And so a reduction. So you can, so this is just a line continuation. But you can say plus sum 1 comma sum 2, okay, with the reduction. And then again, OMP parallel 4. And OMP parallel 4 reduction, you know, same thing, ent 1 and 2. Okay. Here I added this just, you know, because if somehow p is equal to 0, obviously you don't take the log. And that is it. So one common bug, by the way, I'd forgotten about. If you say get num thread, you're requesting how many threads are running, but you have to run this function inside a parallel region, right? If you run this function in the sequential region, you always return 1. Just remember that if you want to query how many threads are running, you got to make sure that you're inside a parallel region. And you know, I want to print this only once, so OMP parallel, OMP single, and then you can print the number of threads assigned to this work. Okay, all right. So basically, this is it. So let's go back here. Okay, so just a couple of things to finish up. So essentially, you know, I'm going from most efficient to least efficient. Okay, so this is so make sure that if you want to implement your code, you sort of follow, you know, into the thinking about what solution to use, follow this order. So first is, you know, is it a reduction? If it's a reduction, you should use that. But there are cases where, you know, you're updating a variable, like you're doing this plus equal, but it's not actually a reduction. Okay, so I'm going to show you a case, in which case you want to do atomic. You want to do atomic, and just put it here. So you want to do atomic. So I'm going to explain how this works. So example I want to give you is n-body problem. Okay, so when you have gravitational bodies interacting with gravitational force, right? It could be also, you know, in a molecular dynamic simulation when you're computing, for example, electrostatic forces. Okay, so basically, if you have n particles, you have n square interactions to calculate. Take all pairs, calculate the electrostatic force, you know, and update. Okay, so so this is what the code essentially looks like, or the, you know, another kind of picture here. So you have to loop over all the bodies in the simulation. Okay, and let's say, you know, you get the blue body, and then you loop, so you double loop, you loop over all the other bodies. So you get this yellow. Then you calculate the interaction between M1 and M2, and then you're going to do like a plus equal on this force, and then a minus equal on this force. Okay. So the idea is each force happens for a pair. So of course you could loop over all I, and then loop over all j, and calculate the force that j exerts on I. That's n squared. But since the force j on I is minus the force I on j, you know, you really want to loop only over the pairs rather than n squared. So the pairs would be n squared over 2. It would be n minus 1, actually. Exactly. n minus 1 over 2. Okay? All right. So, okay, and so you can loop over essentially all the pairs, and then once you have a force, then you want to do plus equal on this guy, and minus equal on that guy. Okay, and so this is clearly not a reduction. Sometimes it's plus, sometimes it's minus. But the problem is each time you do plus equal, potentially you may have different threads trying to update the same memory location. Okay, and so again, this is a race condition, and this needs to be prevented. Okay, and so you use atomic to declare that, you know, the compiler needs to do something special with the code right here. So what's nice about plus equal is, well, this can be done either with a mutex, that's very expensive, but very often the hardware allows you to do plus equal. There's some efficient support in the operating system, maybe even the hardware, to do this type of reduction. Okay? But you know, either way, you need to be careful. And so the way this is done is it goes like this. Okay, so you loop over I, so you do OMP parallel 4, so there's going to be parallelization over I, and then you loop over all particles j from I plus 1 to n. Okay, so basically it's really all pairs. If you know, the other way would be ij and ji, n square. So here it's n square over 2. Okay, then you calculate the relative position of I and j, calculate the force, and then you want to add to I and subtract to j. And so here there is a potential conflict. Okay, so there's actually a conflict both on both I and j. So for both of them you need OMP atomic. Okay, and so whenever you're doing just one memory location update, so basically plus equal, minus equal, star equal, or divide equal, and so on, then you want to use atomic. Okay, and this is going to protect the update of F. But this is, so if you're doing a reduction, don't use atomic because this is quite slow. Okay, if you have a lot of threads that try to update exactly the same variable, it's actually very, very slow. Okay, so here it's kind of okay because the odds that two threads try to update the same F are somewhat small. So there's going to be some potential collisions, but not too many. So atomic is a good choice for this problem.
So what's the difference between using atomic and reduction?
Right. So reduction. Okay. So reduction means that each thread is going to make a private copy, and then there's going to be a sum. Okay. So here, the reason why this doesn't work is, well, okay. First of all, it's an array of I. So let me think about this for a second. Well, I don't know. You could perhaps do this with a reduction on an array, which I don't know if this is supported. That depends on the compiler. But that would be the main problem with reduction here. The fact that it's an array, and but there are also, of course, situations in which the final result is simply not the sum of the partial results. Right? There is no simple relation like that. Right? Reduction means that the final result has to be the sum of the partial results. So here it is actually correct, although you have to work with an array F. But there are situations where this is simply just not possible. But you're correct that I have to double check on reduction, whether you can do reduction on arrays. Well, there's actually multiple problems. There's reduction on arrays. But also the fact that, for example, if you were just updating certain entries in the array, the reduction would be also tricky. Right? I mean, okay, there are various reasons why sometimes atomic is the right choice. Okay, so just to wrap it up, the last final choice is critical. So critical means that essentially this is equivalent of a mutex. So it means that the line of code can be executed in any order, but two threads cannot execute that line at the same time. So for example, here I wrote a program to calculate prime numbers. Okay, so I have a parallel for loop, and then I'm testing, is this a prime number? And this is a prime number, then I'm going to insert it into a set, okay, C++ set. So the insertion cannot be done concurrently, okay? So any order, but insertion one at a time. So you need OMP critical in this example here. Okay, so the code is on GitHub critical.cpp if you want to see what it looks like. Okay, and finally, just to kind of wrap up, in time. So there are a couple of things that I haven't talked about. There is affinity. These are more advanced topics, but when you want to attach a task to a specific core because of memory affinity, these NUMA effects is more advanced. You have target. So target is so William is sort of suffering with targets right now. I guess it's not working. But this is a more recent, well, this is sort of the future of programming GPUs. Essentially, you can program GPUs or arbitrary devices, so it's called target device, using OpenMP. So you can actually run your code on NVIDIA GPUs or AMD GPUs using OpenMP, but this is just OpenMP 5.0, so the support, as you know, it comes with 4.5, but it's very recent, so it's still very hard to get to work. But as compilers mature and so on, this is most likely to be default solution because it's much easier to program with OpenMP rather than writing CUDA code. So right now there's really only CUDA that is really well supported and so on and works well, but the future is really more along the lines of using OpenMP. And then you have SIMD, so I mentioned SIMD, and then locks. There's a way to have mutexes and locks in the Okay, so here you have some examples, specifications, if you want to look at the details. Okay, all right, so I'll wrap it up here. So I'll discuss some applications and example applications and algorithms on Friday. Thank you.